Good morning, everyone. Welcome to this February edition of our FME webinar series. And today we're going to be talking about the different approaches to reading and writing data in FME. My name is Ian Fletcher. I am a senior FME consultant here at One Spatial. I've been an FME user since 2017, and I am a certified FME professional and certified trainer. Before joining One Spatial in 2020, I had 8 years of experience in the oil and gas industry, where I was using FME to do various automations and data translation processes. To begin with, let's take a quick look at the ways in which FME Form can access data and how the methods which have been used to achieve this have evolved over time as the software has developed. We start off in the early days of FME with desktop-based GIS formats such as shapefiles and AutoCAD files. This was followed by tabular datasets and database systems in the late 90s and early noughties. Web-based platforms arrived soon afterwards, with cloud storage of files and databases becoming commonplace. And we can now stream huge amounts of data through cloud-native applications and enterprise systems and tools such as SAP, OpenAI, and Cesium. As different formats have evolved, so too have the ways in which FME has had to adapt to read and write data to accommodate these new applications and functionality. We often work with clients here at One Spatial who require data integration workflows which can combine aspects of the entire spectrum of formats and locations. And so different reading and writing techniques are often required for various components of a problem, all combined within the same workflow. And it's therefore really important that you have a thorough understanding of the different approaches to reading and writing data in FME, as this affects not only where you can access the information from, but also the complexity and the efficiency of the process that you can build once you have connected a workflow to it. It is this choice of methods which is what the bulk of the rest of the webinar is about. And there are 4 options that we're going to look at: readers and writers, feature readers and feature writers, connectors, and API calls within HTTP callers. Looking first at readers and writers. So readers and writers are the traditional and oldest way of manipulating tabular and spatial data within FME, and represent the simplest way to begin to build up a workspace to complete basic translation tasks where the data is likely to be locally hosted. Reader objects are typically used to read in one or more feature types and are most helpful for ingesting data that begins at the very beginning of a workspace, where the file needs to be read in from a static file pathway or perhaps a shareable URL. Similarly, writers are most helpful in simple workspaces where data needs to be written at the end of a workspace, where completion of the data write signals the very end of the process. When a reader object is brought onto the canvas, some pre-read filtering parameters are often listed in the navigator settings. However, readers are by design fairly simple to deploy, as they cannot be set up to dynamically react to other conditions of the workflow. Within the parameters list, you can specify a bounding box within which to select data from if the dataset itself is spatial. You can also select a number of rows for database formats, but generally speaking, if the data needs to be pre-filtered in a more complex way, then another method will have to be chosen, and we're going to look at some of those options later. As well as their simplicity and ease of use for basic applications, the main advantage of readers and writers is the additional control these give you over the order in which data is read in and out of a process. By default, data is read and written one dataset at a time, and the order that this happens is by default controlled by the order that they appear in the navigator from top to bottom. Workspaces are most efficient when the least amount of data is held in memory, and so large datasets should appear at the top of the list so that they are read, processed, and written first. Read-write order can therefore be controlled by dragging dataset readers and writers above and below one another, which can become hugely advantageous when handling particularly large datasets, where small improvements in performance can have a large impact on the total processing time. Turning now to feature readers and feature writers, these perform a very similar task to conventional readers and writers and can process the same file, database, and folder formats, either stored locally or behind a URL. The main difference here being is that they can sit within a workflow and so won't necessarily be the first or the last object on the canvas. Being transformers as opposed to reader-writer objects, their sequencing is controlled by the upstream connections that are made to them, and so they cannot be controlled in the same way as readers and writers can by changing their order in the navigator. Having inputs before data is read in and outputs after it is written out, however, has the advantage over conventional readers and writers of being able to be influenced by and having influence over what has gone before or after them in the workspace. Let's look at this in a little bit more detail now, starting with the feature readers. Setting up a feature reader can be quite easy. Connect the output port of a creator transformer to a feature reader, and you can use these just like a conventional reader with many of the same parameters and a similar looking dialog box. The initiating feature triggers the feature reader to run, meaning that the dataset it is set up to read will only be read into the workspace after the upstream process has completed, and at least one initiating feature has been passed through it via the initiator port. There are a few other key differences here to note compared to a conventional reader. Firstly, the initiating feature or features can have attributes, and therefore these attributes can be used to influence the various ways in which feature readers behave and the features that it is actually used to read into the workspace downstream. The example on the screen here, we can see that a series of geotiffs are being read in by the feature reader from a dataset attribute image file, which is contained within the initiator, which itself is being read in via a catalog spreadsheet. Each initiating feature that passes from the test filter to the feature reader will have this image file attribute, and so a different value will be passed into the dataset parameter of the feature reader, and thus will read in a new object accordingly. This is hugely powerful as it allows for a level of dynamicism unavailable when using conventional readers, where the dataset is being defined at the beginning of the workspace, either by a user or an FME parameter, and thus cannot be changed by upstream processes. In this example, where as the input data changes and the initiating features being passed into the feature reader change also, so too can the nature of what is being read into the workspace at this stage of an automation. The feature reader has several other properties which are helpful when building dynamic workspaces that can adapt to changing input data. Firstly, the schema port, which you can see at the top of the feature reader, allows you to optionally create a schema feature for each dataset without the need for a separate schema reader, schema scanner method. This will create a schema feature for each unique feature type, and this can in turn be used within writers when creating dynamic outputs where the output schema is not necessarily known in advance. The schema of the feature type is described as a list of attribute names and attribute types. Here we can see we have a geodatabase being read in by the feature reader, and this has two feature classes, each of which creates a different schema object that can be used downstream in the workspace. Secondly, similar to how a reader can be set up to create a separate canvas object for each feature type, so too can a reader be set up with individual ports for named feature types for specific processing workflows. You can also have a single generic port, which will handle any data that is read in to the feature reader regardless of its schema. The generic port of a feature reader works very much in the same way as the single merged feature type function of a reader and will allow multiple feature types to pass out of it as a single data set into the downstream process. For workflows where the input feature types can change and the downstream workspaces need to adapt to new data models, the generic port is therefore a really useful tool, as you no longer need to hard code in a specific schema into the reader and writer. All data is passed out of the generic port regardless of this data model and is thus available for processing downstream. Finally, what is, in my opinion, the greatest advantage of using feature readers, which is the spatial filtering of inputs before they're read into a workspace. As a point of best practice, a workspace will operate most efficiently if the least amount of data is read into memory and processed, and thus the amount of data that a workspace needs to read in, it's advantageous to streamline this as much as possible. With that in mind, the constraints parameter set on a feature reader, and in particular the spatial filter option, is an incredibly helpful tool. As I mentioned beforehand, the attributes on an initiating feature can be used as parameters within the feature reader, and in a similar way, so too can the geometry of these initiating features be used to filter the data that is being read into the workspace, which is a really powerful and efficient way of reading in only the data that you need, rather than an entire data set, which you may then be immediately spatially filtering anyway. You can see in this image the predicates that can be used options, and what this means in practice is that the data can be dynamically filtered based on the properties and the geometries of the initiating features. This makes for a really efficient workspace, as it avoids the typical requirement to read in a data set and then filter it before immediately discarding what is not needed. Turning now to feature writers. For the most part, these again act very much like a conventional writer. Notice though that there is also a summary port coming out of the feature writer, which contains metadata about the datasets that you've just written. This is a really fantastic way of triggering a downstream process, perhaps even another feature reader, once the dataset has successfully written, as this port is only activated and enabled once the data writing part of this workflow has been completed. A really common use case for this, as we can see in this example, is to take the output that has just been written and send it as a zipped folder to a specific user using an email or transformer for further processing. Using the summary port of a feature writer is therefore a fantastic way of controlling when a downstream process is triggered, where that downstream process is depending some way on the data that has been written first. Putting this all together, let's just reflect on what this workspace example is doing using some examples of feature readers and feature writers. So we have a catalogue of geotiffs on the left-hand side, which is being read in from a conventional reader. This catalogue of geotiffs covers the entire extent of the city of Vancouver and is a very high resolution dataset which has been tiled into a 6x6 grid, so we can expect the full dataset to be rather large. To speed up the processing of the orthophotos, we are spatially intersecting them using the feature reader with a dataset of historical area zones, which are acting as the initiators in this case. The rasters which intersect historical areas are then being read into the workspace and resampled before being written out to a destination directory. The summary port on the feature writer is then triggering an email to be sent alerting an administrator to the new data, as well as an FME flow resource connector to post that data to an FME flow directory, which can in turn trigger a server-side automation. So looking now at connectors, we've already seen how both readers and writers have the ability to access data on a web-based storage platform such as OneDrive, Dropbox, or maybe ProjectWise, so long as that application can supply a shareable URL to the target file. Using the select from web function, you can either specify a URL or log into a selected list of applications from which to choose a file to read in directly. But what happens if the file that you're looking to access is in an application that does not provide a shareable link, or maybe that file or data is only available through an API, or maybe you don't actually just want to read in the data, maybe you want to delete it or list the files within an online directory instead. This is where connector transformers can be really helpful, and this is the third option that we're going to look at. Connectors are a solution to the problem of interacting with files and data more generally that is held within an online platform that cannot necessarily be conventionally accessed using conventional readers and writers. Connectors are a user-friendly method of packaging up all the key functions of a particular platform's REST API, namely list, download, upload, and delete actions, all within a transformer, which provides a flexible out-of-the-box FME experience. And this is particularly useful for FME users which may not be comfortable for dealing with the complexity of API calls in code. Connectors are available for many of the common cloud platforms that we interact with, and many are built into FME as default transformers, although many more are also available through the FME hub to download or through packages. Each connector typically will have a single input port and a single output port, alongside a rejected port for invalid requests. Within the parameters of the connector, you will see a number of very simple actions that you can take, which reflects the broad commands that you could achieve with the backend REST API request. But generally speaking, the functionality of each connector is quite simplified, as the connector is effectively compiling the API request for you using the transformer parameters as a bit of a template. The great thing about connectors is that they can be chained together to create complex interactions with some of these cloud-hosted applications. So in this example, we are listing files from a box directory using the first box connector. We're then using a test filter to choose the latest file within the box folder. We're then using a second box connector to download that file to a temporary directory, before then using an FME flow resource connector to post it to an FME flow directory for use in another automation. Finally, we're now going to look at HTTP callers, and these share many aspects of the functionality of connectors, but with full control over the particular API requests that you can make to a service, which gives you a huge amount of flexibility to control the way in which data is queried and digested, and input and output, not only within FME but also back to the host application. Furthermore, and importantly, API requests via HTTP callers are not limited to file-based cloud storage applications and can instead access any online application that can be queried using an external API. This is particularly helpful for integrating with many of the common enterprise systems which we interact with in our day-to-day professional lives, such as SAP, Salesforce, Azure, AWS, but they can also access other online tools which allow developers access via an API, so long as these APIs conform to the Open API data standard. HTTP callers will have a single input and a single output port alongside a rejected port, again, very similar to the connectors. The request URL within the HTTP caller parameters can be supplied via an initiator string attribute, thus providing the ability to create an API request dynamically from incoming attributes. Very much like the ability of feature readers to use attributes upstream to define the dataset, this is a fantastic way of constructing dynamic API requests using string manipulation to react flexibly to whatever incoming data is being supplied to it. Looking at some of the other settings here, secure applications will often require authentication, much like many of the connectors, and this can either be managed from web connection systems or by supplying credentials and tokens via the API request header option. API requests can allow you to download whole files and also, but also records within a wider database. And these are supplied to the output port, usually as either a JSON or a YAML response, which can then be fragmented into separate features and processed accordingly. The strength of the HTTP caller is its ability to compile dynamic API requests to any online application it has authentication for, so long as that authentication, as I mentioned, complies to the Open API standards. And so this is a really flexible solution, as it does not require a named transformer to connect to a specific application, unlike the connectors that we've already discussed, where you have one connector per application. Each application will have a set of API commands which is suited to it, and this is typically documented behind a developer portal on the application. So on the screen here, I'm just showing you a screenshot of the Box API, which we can see in this example. API commands conform to certain syntax, and this is described in the API documentation, and this will allow you to string together various parameters, allowing you to upload, download, list, delete, and update entire files, and also records within the application database. Specific APIs might also let you query records by a certain property, move files from one folder to another, or trigger other specific processes within the application itself. The number of options here is infinite because each API is built specifically to work with the platform in question. API requests via the HTTP caller are therefore provide them ultimate flexibility when manipulating online files and records, but it does require some understanding of the syntax and use of API requests in the first place. Unlike connectors, which use the basic functions of an API within an FME transformer, APIs within the HTTP caller give you full flexibility to manipulate the data as it was intended using the native API. Looking at this example here, I'm accessing my personal exercise activity held on Strava, which is a sports tracking application. We are using a GET request to list my last 100 activities. This is returned from Strava as a JSON string, which we are then breaking into separate JSON fragments. We then use a second HTTP caller to find the details of each of these activities, which is tagged as a run, before the data is then written to a local directory using a feature writer and then posted to a shared resource folder using a third caller. Just to summarize then, the choice of reading and writing techniques can have a huge impact on the functionality of a workspace and the efficiency with which it can transform data. Each of the four methods that we've discussed has a variety of advantages and suitable applications that it's designed for, but of course there are also disadvantages too. So readers and writers are very simple, but they're not very dynamic and only can sit at the start or the end of a workspace. Feature readers and feature writers are more flexible in the way that they read in data, but you cannot control the order. Connectors can only produce simple API requests, but do not have the same functionality as an HTTP caller. An HTTP caller has full functionality of an API, but that requires in-depth knowledge of how an API is constructed. So just as a way of wrap up, if the content that you have heard here has been helpful and has inspired you to learn more about FME, One Spatial has a number of FME training opportunities. We run regular training events in FME Form and FME Flow, the details of which you will find in the webinar follow-up correspondence and will also be listed online. We also have a regular webinar rotation, which runs once a month, where you can pick up helpful tips and tricks, as well as learning about some of the latest case studies in innovative FME use. The next webinar is in March and will be on the differences between FME Flow and Flow Hosted.